Thank you to everyone for your presence. Welcome to this presentation titled Toward Empathetic Human-Robot Interaction, a multimodal framework integrating psychological profiling and emotion recognition by myself and my colleagues, Ragno and Zamiletti. Over the next few minutes, I will walk you through our research, which aims to enhance human-robot interactions by equipping robots with empathetic communication skills. Our motivation stems from the observation that empathetic engagement is central to human relationships, driving trust, cooperation, and overall satisfaction in social and professional contexts. If we can design robots that effectively perceive and respond to human emotions, we will unlock new possibilities in healthcare, education, and companionship. Human-robot interaction, HRI, is a multidisciplinary area bringing together engineering, psychology, computer science, and ethics. At its core, HRI seeks to create more engaging, intuitive, and helpful robots, machines that serve as partners in human activities. One critical aspect of HRI is empathy, which in turn relies on accurately gauging human affective states and adjusting robotic responses accordingly. Empathy in machines is more than a technological challenge. It addresses how people can feel supported, validated, or comforted when dealing with non-human agents. Real-world applications stretch far beyond standard industrial robotics, aiming to improve patient wellness in hospitals, student engagement in classrooms, or senior care in assisted living facilities. Why is empathetic communication so significant? Empathy supports a sense of understanding between individuals. Transferring this dynamic to robots can help reduce user stress, build trust, and enrich collaborative tasks. For instance, an empathetic robot tutor could detect when a student feels frustrated and respond with encouraging words or slower-paced explanations, promoting a positive learning experience. In broader terms, empathy fosters a genuine partnership between humans and robots, allowing users to feel respected and heard. This quality can be vital in delicate or high-stakes settings, such as mental health support, social caregiving, or even conflict resolution. Despite its promise, empathetic HI faces significant hurdles. Anthropomorphism, determining how human-like a robot should appear and behave without causing discomfort. Cultural and demographic variations. Emotions are perceived differently across cultures, which means a one-size-fits-all empathy model may not perform optimally everywhere. Real-time, multimodal integration, processing voice, facial expressions, and textual cues simultaneously requires substantial computational resources and algorithmic sophistication. Addressing these challenges demands an interdisciplinary approach that blends engineering expertise with social science insights. Our study aims to create a comprehensive system for empathetic interactions by fusing multimodal emotion recognition. We gather facial expressions, vocal intonations, and textual cues. Psychological profiling. We incorporate disc-based personality insights, which guide robots in using communication strategies suited to the user's inherent traits. By layering time-invariant data, e.g., a user's personality type, with time-variant inputs, e.g., momentary emotional states, we can generate appropriate responses that reflect both who the user is and how they feel in real time. At a high level, our system identifies individuals via facial recognition, builds or retrieves a psychological profile using the DISC model, analyzes user emotions from facial expressions, vocal tone, and textual content, fuses the above data through a fuzzy logic approach, emphasizing signals that are harder to mask, like nonverbal cues, generates empathetic audio or text output. The end result is a robot or digital agent but tunes its demeanor to user needs, ensuring more supportive and empathetic interactions. In the next slide, you will see an example of face identification. Our facial recognition module uses a database of known faces. If it detects an unknown user, the system prompts for their name. This ensures that each user's emotional and personality profiles are tracked individually. Next, we incorporate DISC, the dominance, influence, steadiness, and conscientiousness model. This personality theory segments human behavioral traits into 4 quadrants. D, dominance results-driven, prefers concise, direct communication. I, influence social, enthusiastic, receptive to expressive engagements. S, steadiness prefers stability, thoughtful conversations, and reassurance. C, conscientiousness fact-oriented, detail-focused, values thorough information. By parsing publicly available social profiles, e.g., LinkedIn, the system can glean an approximate personality outline, although this depends on data availability. Beyond the 4 major DISC factors, each dimension can contain subtypes. For instance, a high D user might exhibit more directive language, whereas a steady, high S user may lean toward calm and cautious communication. With such insights, the system chooses appropriate vocabulary, pace, and level of detail. A potential scenario: if a user is strongly dominant and somewhat impatient, the system avoids lengthy explanations. In contrast, a conscientious user might appreciate extra nuance and references. This level of customization significantly elevates user satisfaction. Emotional state detection begins with the face. Face detection: reapply MTCNN, identifying faces in video feeds. CNN-based classification: each face is then examined for key emotional keys like happiness, sadness, anger, fear, disgust, surprise, or neutrality. Facial expressions reveal spontaneity, often offering a more genuine glimpse into a user's feelings than purely text-based communication. Audio data forms the second pillar of our emotion recognition. Feature extraction: we rely on Mel-Frequency Cepstral Coefficients, well suited to capturing vocal intonations. Classification: support vector machines help map these audio features to emotional states such as calm, happy, sad, angry, or surprised. Since vocal changes can occur unconsciously, audio cues often reinforce or counter facial cues, deepening our understanding of a user's mental state. For the third channel, textual analysis, we incorporate advanced language models like ChatGPT-4. Semantic context: the system parses user statements, searching for emotional markers. Sentiment analysis: probability distributions align text with recognized emotions. The synergy of facial, vocal, and textual data strengthens our confidence in emotion detection and interpretation. We unify these 3 emotional analyses via a fuzzy approach, assigning higher weight to facial and vocal cues because they are less consciously controlled. This aggregate probability vector draws a nuanced emotional picture. For instance, if text is neutral but facial expressions suggest frustration, the system interprets a potential mismatch, inferring that the user might be masking meditative emotions in text. After analyzing the user's disk type and current emotional state, the system crafts tailored verbal responses. Our text-to-speech engine modulates tone: softer if the user is stressed, more energetic if they need motivation. Pace: slower when emotions run high, to convey reassurance, or faster when addressing a user who prefers concise answers. This adaptive speaking style transforms standard robotic speech into supportive dialogue, aiming to lower the user's stress or heighten their engagement. Got I in the next slide, you will hear a dialogue where an engineering student will ask a question to an emphatic robot that will respond emphatically.
Hi, how are you?
Hello! I'm just a computer program, so I don't have feelings, but thank you for asking.
No problem.
Is there anything else I can assist you with?
Early testing shows our framework significantly improves user satisfaction and perceived empathy. Participants reported feeling acknowledged and understood. Nonetheless, certain constraints emerged. 1. Reliance on social media data. Some users do not maintain robust LinkedIn profiles, limiting disk accuracy. 2. Latency. Processing is largely cloud-based, so slower hardware or poor network quality can delay responses. 3. Cultural nuances. Emotions can be expressed in ways that differ across various backgrounds, requiring more specialized training data. We recognize that social media data is not foolproof, it may not reflect the user's true behavior. Additionally, the system's complexity can strain real-time responsiveness, especially if hardware resources are limited. Finally, cross-cultural validity remains a challenge, as our machine learning models must handle diverse emotional expressions. Despite these issues, the results are promising, suggesting that robots can be empathetic in practical settings when given the proper tools. Ethical concerns figure prominently in any technology handling personal data. Data privacy. We comply with regulations such as GDPR, ensuring transparency with users about data collection and usage. Psychological profiling. Because we derive inferences about personality, we need to handle potential biases responsibly. User consent. Individuals should remain free to opt out, especially in sensitive areas like healthcare, mental health, or social care. Implementing robust data governance policies and user consent mechanisms essential to the responsible deployment of empathetic robots. Future directions can involve enhanced profiling. We plan to combine multiple data sources beyond LinkedIn for greater accuracy. Edge computing. By offloading processes from the cloud to local hardware, we aim to shrink response times. Expanded testing. Conducting more extensive field studies across different cultures, age groups, and industries. Adaptive learning. Enabling robots to refine their empathetic responses over time as they gather more interaction data. Tackling these improvements could push empathetic robots toward mainstream, real-world use. To summarize, we have presented a novel HI framework that integrates psychological profiling via DISC to adapt to individual personality traits, robust emotion recognition across facial, audio, and textual domains, fuzzy multimodal fusion emphasizing nonverbal cues, context-aware verbal output shaped by user personality and current emotion. Our results indicate that such a system can improve the quality of interactions and create a more supportive, human-centered experience. While limitations persist, our project paves the way for more intuitive and engaging robotics. Thank you for joining me today. I hope this presentation has clarified our approach to delivering empathy through robotics. We believe that with continued research, we can refine these methods and ensure that future robots assist humans not only functionally, but also emotionally. I now welcome any questions or reflections you may have.